so today I have a Razer Blade 15, and there's many variances of the Razer Blade 15 on the 2018 and 2019 model. There's a few different board versions. I'll let you know what this one is in a minute, as I don't have the number recognized on this one yet. Usually I get a ton of 2016, 2017 devices, and just like back in 2016 and 2017, I was getting a ton of 2013 through 15 devices. So I just started having 2018 and 2019 motherboards show up here regularly, and I've seen at least 3 or 4 different versions of them. So yeah, I will let you know the model number here in a minute. But this device came in and it will not turn on. So the very first thing I wanted to do was remove the board and actually check some of the voltage rails. So this is a very similar layout to the Razer Blade 14 2016 and 2017, even though this is the 15-inch model and they changed the color of the solder mask to black from green. It's still a very similar layout. So with the multimeter here, if it's in view, we're going to check some voltage rails here. So one probe on ground. Now these are our main power FETs connected to the charge controller, and they're DPAC MOSFETs. So this big pad here is going to be the drain, 20 volts. So we 20 volt source, and this will be the gate. I see 25 volts gate drive, so we know our charge controller is functioning properly, and that MOSFET's probably good. And this is just our battery MOSFET here. There's really no sense in checking it, because we don't even have a battery connected, but we can see it's a 25 volt gate drive and 20 volt drain and 20 volt source. So that MOSFET's perfectly good. Charge controller's working, that rail's there. We have 5 volt rail there. I check on these inductors right here because it's easiest, but there's a IC on the back of the board is just a voltage regulator for the 5 and 3.3 volt rail, which generates the voltages internally. 3.3 volts, so we know all those are working. Now those are our always on voltage rails. We'll have our 20 volts and our 25 volt gate drive, and then our 5 volt and 3.3 volt. And of course when we hit the power button, we'll have other rails engaged, such as the ones for the DDR memory. But this is DDR4 here, so it'll be 1.2 volts. And we'll have the voltage for the CPU, vCore, GPU, PCH, and things of that nature when the power button is pressed. But our always on voltage rails are present, so we know that's good. So the next thing I did was I disconnected power, and since our main voltage rails are here, there's no need to look there. But what I wanted to do was just start looking over different areas of the board and see if there's any area where, maybe perhaps there's a short to ground in some area of the board that's on a rail, which may not be an always on rail, and that could be preventing it from powering up, because I was getting no green light on the machine, nothing, it just wouldn't power on. And what I found was, from just probing around on each side of the board, is I found a fuse right here, which if you look here, it's pretty close to the ITE, so this rail may be going to the ITE. I'm not 100% certain, but I could find out here in a minute. But the ITE is just like a really complex microcontroller. It does many things from, for example, charge management and stuff. It talks to the charge controller, which talks to the charge controller and main battery pack. It can control the fan and many other things it can do. It has many general purpose input-output pins, which can be configured for multiple purposes, but basically it controls tons of sensor data on the machine. And it's very important to have the ITE working, or the board won't power on. It has some complex firmware in there that handle many operations. But this fuse right here, see, okay, we're getting quite a high resistance on that. This fuse is totally blown. The very first thing I'd want to do is remove this fuse, and then a diode mode measurement. You gotta do a diode mode measurement, which is you put for checking resistance. You put one probe on ground and the other probe on each of the pads that the fuses were sitting on after you remove it. If you do not do this, you will have absolutely no idea if there's a problem in the circuit or not. In most cases, these fuses don't just blow for any reason. They have a very specific current rating, and there's ones which are fast blow and slow blow. But if you go over that current rating, depending on which type of fuse it is, for either a transient, real quick spike, or for extended period, if it's the slow blow kind, then these fuses will blow. So like I said, these things usually don't just blow for no reason. There's probably something else in the circuit which is dead if that fuse is blown. Sometimes a fuse will blow, and there'll be no damage in the circuit. That's if it actually does its job and it blows before it prevents any damage. Sometimes they actually blow because of damage. For example, if there's a short to ground on the rail. No way to really know until we remove the fuse and do a diode mode measurement. So let's go ahead and do that real quick. See, my tweezers are pretty worn down here and burned. It's about time to get a new pair. Alright, our fuse is removed. Now let's check and see if we have a problem. So, diode mode measurement. Let's find a good ground. We can go right here. Oh, let me show you the multimeter. Now, the fuse pads, let's see. That side seems to be normal because it has a resistance. Ah, this side right here is ground. Do you see that? So, usually one side of this should not be ground on a fuse. So, we do have a short to ground somewhere on. Now, I could be looking for this short on this rail all day long. So let me show you what you guys what I do just to help speed things up. We're going to hook up our DC power supply and inject a little bit of voltage into that rail and limit the current and watch the current draw and see if anything gets hot. Plug this thing in. I just wanted to mention something before I mentioned the ITE because it was pretty close, but the more I take a look at the circuit right here, it looks kind of like a PCH circuit. I'm wondering if this is the controller for PCH, and I'm wondering if that is what is shorted and bad. So if we turn this on, we're going to find out if it gets hot. I just hooked it up. This is actually a power wire. Ignore the fact that it's black. I just know what I am connecting to it, and it's not a permanent wire, so it doesn't matter. And then I just used a common board ground over here for this other one, and that'll work. So let's see. Make sure voltages are turned down all the way. Same with current. Let's power it on. And hold on, guys, we're not plugged in. You plug it in. Power it on. Let's give it just a little bit of voltage. If this is PCH, it's probably a 1.05 volt rail. So I do not want to give it much voltage. Whoa. You can see it's already pulling a substantial amount of current. And I mean substantial, so I'm going to be cautious here. Alright, there is half an amp. Whoa, guys, we're already almost at an amp. Something's getting pretty hot here, so let's back that down a bit. So whatever is bad should get hot in theory, so let's take a look. Alright guys, so it does look like that controller is bad. I did get a little bit burned on it, but just to kind of show you, if you put alcohol on it right here, I don't know if you can even see it, it bubbles right off. So what I'm going to do at this point is shut off our power supply, and I'm going to remove that chip, and I'm going to see if we still have a short to ground. If it's gone, then we know that was a chip. So I just removed that controller, and if we measure, we still have a short to ground, which is interesting because this chip did heat up. So if we measure around, we can see it's on these capacitors here. There's a short to ground. So okay, perhaps one of these capacitors is also shorted in addition to this IC here. Let's measure around a bit. Okay, so we know everything here is on this the right side of this inductor. Because up here we don't have a short to ground. Over here we don't, but we do on these capacitors. So let's see up here. No, we don't up here either. That's just a low resistance rail there. That's fine. What we have down here is a total short. Let's see over here. No, that's fine. Okay, that's fine. So basically everything is just over here on this side of the inductor. Let's flip the board over and take a look. So right around that area, yeah, there's nothing under that memory chip. Right around that area is right around here in the PCH area. So let's take a couple more measurements just to check. Now this will be for the GPU circuit up here. That's good. Let's see. That's probably okay. Yep, that's the low resistance rail, but it looks like it's fine. So basically everything seems to be okay. So it's just isolated to that one little area. But there was definitely heat coming from this area right here. So I'm going to guess and say maybe one of these capacitors were also bad. So let's go ahead and remove them. So I removed these 3 capacitors here. Now let's just take another reading. Well, there's not a short anymore. It's reading as open circuit, which means that one of those 3 capacitors were actually bad. Not sure which one, it doesn't matter. One of them was bad, and possibly this controller as well, because it was getting hot. And probably what happened was, yeah, the heat was probably just spread out right around there. I probably didn't detect it initially on those 3 capacitors because the wire was kind of in the way and blocking that, and I just noticed that this controller got hot. And so, yeah, anyway, there's a good chance that all those were bad. But it is the short is removed, so let's see if I can replace this controller, these capacitors, and then recheck these pads on this fuse to see if it's still good. If it's good, I'll replace the fuse. Then we'll see if the device turns on. Okay, it just flowed into place. Make sure it's soldered well. There we go. Perfectly soldered. Now, as far as those capacitors go, when in doubt, if you have no way of knowing what was there, it's usually good to go with a higher capacitance than needed in most cases. But I'm going to see if I could actually measure those. Just let me check this again here real quick. Okay, look. We don't have open on that one pad now because the controller is placed down. And we have resistance on each side of this fuse pads. So we're good. Just need to replace those capacitors. Now, for checking these capacitors, this meter has a capacitance mode. Now, obviously, the capacitor has to be removed from the board in order to test capacitance accurately. But we have 3 capacitors up here that I just took off the board. Let me see if I can measure. So we know at least one of the capacitors isn't bad, and it's giving us 10 microfarad. Alright, so I decided to put a larger capacitor Case size on this first one, this is an 0603, but it fits fine on a 402 pad here. And this is a 25 volt 22 microfarads. And then I put just two 0402s on the other two pads. One was a 10 UF and a 0.1 UF. So the idea behind this is I had no idea really specifically what value those other capacitors were. I knew one of them was 10 microfarads. I don't know what the other ones were because they were shorted. But using a varying case size and different value rated capacitance just gives you a lower ESR over wider frequency range, which, I mean, for most controllers like this, I would imagine would be desirable. Because it's reading open, but that's probably because that controller is open. We're going to put a fuse on there and see if it powers on. Alright, as you can see, the fuse is on there. I'm just going to clean up this area with a little bit of rubbing alcohol, isopropyl, just to remove a little bit of flux that I used to put the components on. It's no clean flux by Amtech anyway, but I like to clean them off if I can. I'm doing a very minimal install just to test this before we you know, waste too much time in reassembling if there's something wrong. So I'm just going to plug this in. Alright, I'm going to hit the power button. Let's see. Alright, there's actually a good reason it just didn't power on. I forgot to plug in the charger. I gotta plug it in the wall. Hold on. Oh, we got a green light for a second. Before, we didn't get any green light at all. Now it's blinking. Let's see what happens. Sometimes after being just repaired, it takes a minute to turn on the first attempt after repair. And then subsequent turn-ons will just be normal after that. So let's see if it's going to turn on for us. Green light's still blinking. Oh, there it is. Look at that. Now there's no SSD in this machine, so it's not going to boot up into the operating system, but you can see it is working. So I'm going to do the rest of the install of this board and do a final test to see if everything is perfect before I consider it a 100% successful repair. So that'll be all for this video. We just repaired a Razer Blade 15 2018. So thanks for watching.